Hello everyone, welcome to Pratibha Tech. In this video, we will solve the problem of the day question on Geeks for Geeks for 26th March 2023. The problem statement for today is frogs and jumps. This problem is based on mathematical operations and array data structures. And this has been asked in PayPal interview. Let's now open this problem to solve it. Let's go through and understand the given problem statement. Here it is said, n frogs are positioned at one end of the pond. All frogs want to reach the other end of the pond as soon as possible. The pond has some leaves arranged in a straight line. Each frog has the strength to jump exactly k leaves. For example, a frog having a strength 2 will visit leaves 2, 4 and 6, etc. while crossing the pond. So the total number of leaps covered by a frog will be directly dependent on the strength of the frog given in the problem. So further it is saying that given the strength of the frog of each frog and the number of leaves, the task is to find the number of leaves that may not be visited by any of the frogs when all the frogs have reached the other end of the pond. So here the problem statement is simple. N frogs are there. They are at the one end of the pond. They want to go to the other end. So for going to the other end, they have some leaves to which they can jump on and they can hop to the other end. So we have to see how many leaves are left that were totally unvisited by any of the frogs. So we have to find that count. Number of unvisited leaves in the pond by the frogs when they are crossing from one end to other end. I hope the problem statement is clear. Let's go through and understand the given examples. Here the input is 3, that means number of frogs is 3, leaves there are 4, and the strength of each frog is given as 3, 2 and 4. So here the output is 1. Here it is saying that leaf 1 will not be visited by any frog. The reason for that is the strength of each frog is greater than 1. That's why for any of the frog it was not required to visit one then to visit the other one, because they want to reach the other end as soon as possible. So they will utilize their maximum strength to reach the farthest leaf possible for them. So for the frog 1, so the farthest leaf it can reach in one jump is 3. Similarly, for the second frog, the farthest leaf it can visit is 2, and for this one, for the third frog, the farthest leaf it can visit is 4. And here we are saying the total number of leaves are 4. So the first leaf is not attended by any of the frog, because that will in that case, if any frog visits that one, then they might not be utilizing their total strength, 100% of their strength, and they had to reach the other end. That's why it is saying that leaf 1 will not be visited by any frog. Let's go through and understand the second example. Here number of frogs is 3 and number of leaves is 6, and the strength of all 3 frogs are 1, 3 and 5 respectively. So here the number of unvisited leaves will be 0. The first frog will visit all the leaves, so no leaf is left unvisited. The reason is that the strength of the first frog is 1 only. So that frog has to hop one leaf at a time. That means first it will go to the leaf 1, then from there, since the strength is 1, then it can only go to leaf 2, then from leaf 3, leaf 4, leaf 5, something, and leaf 6, something like that. So all the leaves will be attended by frog 1. That's why here the output will be 0, because none of the leaves were unvisited. I hope both the examples are clear. So to solve this problem, we will use a different data structure. We will use BitSet data structure to keep the track of unvisited leaves. So I'll tell you what is BitSet data structure. So in Java, a BitSet is a class that represents a fixed size sequence of bits, each with bit having a value either 0 or 1. It provides a convenient way to manipulate sets of bits and perform bitwise operations. So let's understand this data structure better with one example. So this way we create an instance of BitSet. BitSet is the class which is provided by java.util. And here initially we have defined the size as 8. So, and what we are doing here, we are calling the method bitset.set, and we are passing the value 1, 3 and 5. So what it does, see, the bitset can only store the value 0 and 1. That means internally the value. So what it will do, it will set the value at index 1 to 1, from 0 to 1. Similarly, the second statement, it will set the value at index 3 from 0 to 1. That means it is setting the bit. Similarly, for 5, it will set the value from 0 to 1 for index 5. Okay, I hope this is clear. So if I try to add something more here, bitset dot, see then we can see here, where is the set method? See, we are calling this set method, and what we are passing the bit index which we want to set. So if I pass here 7, so it will set 7. Okay, so it will set the index 7 value from 0 to 1. So now remove this, and we'll go with this example only, because I have further more thing to explain. So here we can see here, for this we have got our output as 135, this one. Another thing is that if you want to clear the bit, that means if you want to unset the set bit, then we have to use clear functionality. So what it does, it changes the set value from 1 to 0. So if I use this one, then if I try to now comment this one, this was for some different purpose, I'll explain that as well. So if I try to run this one, then see the second output. So here it is 1 and 5. 1 and 5, because now we have cleared the set bit at index 3. Now that bit is now unset, in unset value. So that's why what all index values are in set mode right now, 1 and 5. Another thing is that if you try to give duplicates of this one, then it will not perform. It will clearly set, it will check that this value is already set. I hope this is clear. If I try to set this one, then it will check that this value, the value at this particular index is already set. That's why it will completely ignore. So even if I add 5 again, it will give the same output as earlier, because it will completely ignoring that. See, here still we are getting 1 and 5 only, because we have unset 3 here. So second example, this one. So now another thing, so this is the another example. So that was not needed actually. One example is sufficient. So what we can do, see, another method we can use here is, here what is the variable here, let me print here system sysout, here bitset dot bitset.cardinality. Oh, here the spelling is, the object name is this. So if you use this bitset.cardinality function here, then see what it does. See, it will count the number of set bits if you use this bitset.cardinality functionality. So this was having 1 and 5, so that's why it printed 2. If I copy this to here, then see, we will get 3 here, 3 for the first one and 2 for the second one. So we are getting the cardinality. Cardinality means it will count the number of set bits. So here it was 3 and next time it was 2. So what we will do, we will use this functionality, that means this approach only, this data structure only to solve this problem. So I'll just explain it line by line that what all steps are involved in the solution of this problem. So instead of typing the solution here, I've already prepared it. Let me just copy it, then I'll explain it line by line. Control A, Control C. So here, like all other previous solutions, I have also tried giving the comments here so that it becomes self-explanatory. So here, so what we are doing here, first one, this line is creating a BitSet object named visited with the size of leaves plus 1. Then the way I have explained, a BitSet is a class in Java that provides a set of bit value either 0 or 1, which can be used efficiently to store and manipulate the set of Boolean values. The visited BitSet will be used to keep track of which leaves have been visited by the frogs. So this is the purpose of this one. Then what we do, then we iterate over each frog in the frogs array. For each frog, it first checks if the frog position is less than or equal to leaves. See, because if it has already crossed that leaf, that means the total number of leaves given, then there is no scope of visiting any other leaf. Either it has reached the other end or it is somewhere in the middle only, but it cannot have it cannot have a scope of visiting any fresh leaf, further leaf. That's why this condition is there. So we will check that if the frog position is less than or equal to leaves, and if the leaf at that position has not been already visited. So for that we are checking that visited.getFrog. We are checking that set value of that bit set array by passing that index and that value of the frog position, and we check if it is not been visited. If both the conditions are true, then it enters inside the loop, and that starts at frog's position and increment by frog's position, that is equal to j plus or equal to frog. See, because in the question the frog strength has been given. So if a frog is on leaf number 2, so the next iteration for the leaf it will be for a 4 only, because the frog will jump on its maximum strength so that it can reach to the other end maximum, so that it can reach other end as soon as possible. That's why we are initializing with the frog position and incrementing by frog's strength. That means frog's position or strength, whatever you can say. Okay, until it reaches leaves, until it reaches all the leaves. At each iteration of this loop, it sets the bit corresponding to the current leaf to 1. So this one. So whatever the index position, whatever we are passing for this one, so what it does, it will set that bit in this BitSet data structure. Why we are doing so? This will indicate that the leaf has been visited by a frog now. I hope this is clear. Then after all the frogs have been processed, then we enter inside the loop to count the number of unvisited loop, iterating over each leaf position from 1 to leaves, checking that if the corresponding bit in the visited is set to 0. So we'll get the value is here. We'll get that value of that the set value of that particular index, and we will check if that value is that if the corresponding bit value in that visited bit set is 0. Okay, if it is 0, that means that leaves has not been visited. So the number of zeros we get in this BitSet data structure, we will keep on adding that. So according to the first example, here only 1 was the one visited. So it will iterate through all the leaves. So here when the leaves value will be 1, that time it will see that the bit at index 1 in this BitSet data structure is still 0. So it will count unvisited as plus, that will increment unvisited value from 0 to 1. Okay, so once all this iteration is done, then it will simply return the unvisited. I hope this is clear. So now let me try compiling this code. So we have got our correct output here. Let me first try submitting the solution. Then we can try using that cardinality functionality here. So see, we have got our correct output. All the test cases have been covered. So now what we can do, we can try using that cardinality functionality which we have seen in this example, in this one, cardinality functionality. So for that, what I'll do, I'll comment this piece of code, and here see that cardinality will give the number of leaves that were set to 1. Okay, so what we'll do, we'll first subtract that from number of leaves minus Control C visitor dot cardinality. I hope I've given the function name correctly. Let me try comparing this code. Yeah, so yeah, this, so see, instead of using this iteration and keep checking each index, we'll simply count how many leaves, that means how many indexes in that BitSet array that represent the number of count of leaves, how many leaves were set. So from the total number of leaves that were present, if we subtract the number of leaves were set, that means the number of leaves were visited, so we simply get the unvisited count. Simply we return that. Let me try submitting this solution. So even with visited.cardinality functionality, it is working as expected. So this was the Java solution of it. Let me try giving the C++ solution, corresponding code for a C++ for it, because of the viewers asking for it. So here the same code I have prepared. Control C. So here also everything is same only. Here we are initially setting the bit set to a large number of a large value, so that it can cover all the test cases. Apart from that, everything is same. All the things has been same the way we have set in Java solution. Same thing here. Again we are counting first here. Then we will try to replace it with the corresponding count functionality of the bit set in C++. Let me first try with this, compiling this C++ code. Okay, this is fine. So let's try submitting this. So see, even this is working fine. So let me try that cardinality functionality here. So here let me comment this, and here we will do the same way whatever it was done in Java. So leaves minus here it was visited. See, but instead of using cardinality, that was for Java, the corresponding function of cardinality in C++ is count. The functionality same here, it will count the number of set bits. Let me try compiling with this. So this is fine. So even with this count functionality of the BitSet data structure, this is working fine even for C++. So I hope both the solutions in C++ and Java both are very clear. Okay, so let me try removing this. It's not needed. So it has become more concise now. Okay, so talking about the time complexity of this solution, it is in the order of n log leaves, where n is the number of frogs and the leaves in the maximum number of leaves. I hope this is clear, that n is the number of frogs and leaves is the maximum number of leaves. This is because the algorithm iterates over the frog in the array, and then it checks and sets the multiples of the frog using the bit set data structure, which has the time complexity of O of log leaves. Therefore the total time complexity becomes big O of n log leaves. So first it will iterate for the n, this outer loop will iterate for n time, and the inner loop will iterate for log leaf times, because we are not iterating for all the leaves, we are keeping a jump of the frog. So that's why the overall time complexity becomes big O of n log leaves. So I hope this is clear. So I'll provide the link for this question in the description box. Please do check that. That's all in this video. Please like, comment and share the video, and please subscribe to the channel for more upcoming videos. Thank you for watching.